day, we get a little experience with conservation laws. So when we say a quantity is conserved, we say it doesn't change. Momentum is one of these quantities that is often conserved, and again, it becomes a powerful tool for us to understand the physical system and the physics of what's going on. So, under what conditions is momentum conserved? Well, really, what we're talking about are conditions when the change in the momentum of the system is zero. And if you recall, what this really implies is that the impulse imparted, that is J, by all of the forces when we add them together, gives us zero. So the total impulse imparted on the system has to be zero. Okay? Another way to say this is that delta P, which is the net average force exerted over some time interval, if the net average force times the time interval at which those forces act, if this is zero, then our momentum change is zero. Now, this is a vector quantity, so we have to keep in mind that I'm going to often want to think about delta P, which is P final minus P initial. I'm going to want to think about that as a vector expression. So if the change in momentum is zero, this implies that my final momentum is equal to my initial momentum. So when I imagine my system, I add up all the relevant momenta. Maybe it's a couple of balls that are rolling around, billiard balls. But I may want to break this down into maybe x and y components. That is, P final in the x direction has to be equal to P initial in the x direction. And then P final in the y direction is P initial in the y direction. And those things are equal separately. So if momentum is conserved, it's conserved in the x and the y directions, which means we really have two equations that help us solve problems. Okay? Now, I don't want you to memorize equations. The only thing you really have to understand is that this is the condition for momentum conservation, and then you apply vector analysis. Now, the other point that I just want to make as you get comfortable with this material is when you think about a collision, right? We say that momentum is conserved in a collision because the collision happens so fast and none of the other forces that are external, even if it's friction, they don't impart a whole lot of impulse during that time. So in a collision, the momentum is approximately conserved, and so a collision of two billiard balls cracking off each other, maybe a car collision, maybe mud sticking to a ball, I don't know what it is. But even if you can identify forces that are external, that are acting on the system, like friction, okay? In a collision, either delta T is really, really small, or the force is really small compared to any changes in momentum that we might see. So, this is just by way of saying that we're practicing the art of approximation here, that in a lot of physical systems, momentum is approximately conserved, and so we can use that idea to try to understand the system. Come to me with any trickiness, but have some fun.